First, let me remind you that DESI is a spectroscopy survey. Its main intention is to measure and observe about 40 million galaxies in its 5-year operation. And basically, when I said that this is an spectroscopic survey, what I mean is that it not only observes galaxies, stars, and quasars, but also it has a very good determination of the redshift of these objects. So we have a 3D position of this in the sky of these objects, and the way that we quantify the redshift is through a very high resolution identification and detection of the spectra of these objects. And therefore, our idea is to improve the way that we measure these redshifts and reduce all the source of contamination that could cause variation in this quantity. So, as I said, to see the Dark Energy Spectroscopic Instrument is positioned in the Magellan Telescope in Arizona, and it's going to measure about 14,000 square degrees in the sky, in the northern sky. And it's gonna focus on the observation and spectroscopic confirmation of galaxies, stars, local stars, but also very distant quasars. Ideally, we plan to get about 3 million quasars in this 5 years operation, but right now with the early data release that was made in June, we have observed about 400,000 quasars at different redshifts. So the way that I'm going to proceed in here is not by using directly quasar spectra, but instead we have produced a set of synthetic spectra of these objects. But let me first give you an idea of which kind of spectra we're planning to, or we're using, and are going to keep using to do a forecast of the future observations of this telescope. So let's say that here we have a typical quasar spectra. So we have the laminal emission, some metals, a redshift from laminal emission, and then we have a bunch of absorptions with different equivalent width that determine the interaction of the light that was emitted by the quasar and the objects that are in the path of this light before it reaches our telescope. So, for instance, typical features are DLAs, damp laminal absorptions, and also I'm not showing here broad absorption lines that are the main focus of this talk. And here I'm just showing a typical quasar representation that was made by Robin Deal, and it shows what we think are typically these quasars that are after galactic nuclei, very few inside the center of the galaxies. So these very bright objects emit a lot of photons, and we try to capture them by observing them. But of course, this is a very random process that it's also due to the anisotropy in the matter distribution that we observe, at least at small scales, cosmological scales. But what I'm trying to leave you here is with the main idea that we have of the main picture we have of these quasars, very bright objects. Also here, we can see that there's the typical absorption path in the light that it's going through different structures before it reaches our telescope. And once the light is emitted by the foreground quasar, what we have is that this light is absorbed by different structures, matter structures. And so we see this Lyman alpha forest that is typically seen in quasars after reionization. So if the light has been emitted after redshift 6 or so, we're gonna see these very dense absorption lines in the foreground quasar. So let me move to the results of this work that was done in the Lyman alpha working group. But first, let me explain what is a broad absorption line. It's typically a line that is seen blue shift from particular emission lines as carbon-4, silicon-4, Lyman alpha emission, or nitrogen-5. It has been also associated to other emission lines, but in particular, I'm going to focus on broad absorption lines that occur blue shift from carbon-4 and silicon-4. And the thing that this line has is that they absorb most of the flux that it's found blue shift from these emission lines. So this is going to change the continuum, and because of that, it's going to produce a misclassification of these quasars, this spectra, and also it's going to produce an error in redshift. Because of the inner nature of this telescope, that it's focused in particularly on the spectra, having these error redshifts is not going to help us to improve the precision in which we classify and measure this very important quantity for the classification of these objects. That's why we need to reduce to the minimum these errors that are causing a misclassification, and that's why we plan to, or we did some mask of these bulk lines. Here I'm showing two examples that were produced based on templates that were made with SDSS. And what is important here is that in previous work from Google and Martini in 2019, they reported that 16% of these quasars are going to have broad absorption lines. And depending on how wide are these absorptions, that is going to cause a larger error in our predictions. So what we did is that we generated a large sample of quasars, and from then 16% of these quasars were implanted with a BAL. These BAL troughs are going to be introduced randomly, so we're not generating any bias in our analysis. and they were implemented bluer from carbon-4 and silicon-4. The interesting thing about this way to proceed is that we don't really need to observe in advance this spectra in order to anticipate what is going to be the outcome and at some level, what it's going to be the improvement if we mask the broad absorption lines. So I'm just going to focus on these 4 emission lines, and the rest frame wavelength is reported here in the second column. So again, why do we care about these absorption lines? Mainly because they are causing a misidentification of the redshift, the true redshift of each spectrum. And as you can see here in this histogram, let's assume that we know the true redshift of a quasar. If we feed the redshift with the redshift classificator red rock in red, we actually see a bit of variation. But then if we also introduce broad absorption lines in the analysis, that is going to cause a difference in the redshift that it's estimated by red rock, even if the classificator is making a very good job, it's still going to have some error associated to the presence of the body. So what we did is that we used 2 samples, one with only Lyman alpha without introducing the VILs, with 4 different exposures, 1,000 to 4,000 seconds each time. And then we also introduce randomly 16% of these quasars. We're going to have VILs. And in total, we have 116,000 synthetic spectra with redshifts between 1.8 and 3.8. And that's the redshift where we prepare this spectra, but then with them, we're going to introduce 16% of Val quasars in our analysis. Knowing that, you can see here that these broad absorption lines might have a number of components. For instance, here we have 5 different components. And what I'm showing here is the inverse variance, the flux, and the template that was used to produce this broad absorption line here. Same case here. Here we have 6 components that add up to the broad absorption line that you're seeing here. Is not very pronounced, but then you can see clearly from the inverse variance that if we set the inverse variance down to 0, the redshift classificator is going to skip it, and then it is not going to cause a redshift error. So we did that for all the spectra. We first look in which band was going to fall. Let's remember that we have 3 main bands that are used in DESI. And we also redshift these different synthetic spectra. Another case here, and a particular case where the broad absorption lines might fall in the interception of 2 channels. So once we mask the broad absorption lines in our sample with this parameter different than 0, that determines more or less which is the equivalent width of these broad absorption lines, we find that there is an improvement, a remarkable improvement in the number of quasars that are wrong classified. So basically what I'm hearing is that I'm assuming that the estimate of the redshift for quasars that don't have a broad absorption line is going to be my true redshift, and then I compare that with the estimation for the sample with broad absorption lines in red, and then the variations with the mask broad absorption lines. And as you can see here, there is a notable improvement, and also in particular for quantities that are blue chip from the true redshift. Then if we look at this, we also have a notable improvement in the different percentiles that we consider here. And this is the original visualization that we were using to compare with the scientific goals that DESI made in 2016, and now we have here a very large scatter. But then if we reduce this to the percentiles, we see that there's a difference in the amount of wrong redshift errors. We also quantify the number of poor fits with different metrics. In particular, we use this threshold of 5% in order to quantify the variation and the improvement in the fits that we were doing with RedRock, the classificator RedRock. And then finally, we quantify how many good fail, miss opportunities and lost opportunities we have if we introduce this masking in the regular procedure. And what we see is that there is an improvement of about 1% in the number of fail fits, and then the number of catastrophic errors also reduces notably if we introduce this masking in the regular procedure that is going to be used with true spectra. Thank you so much, and I'll leave you with these conclusions.